So hi everybody and welcome to this 8th video in the solutions chapter. So in this video we'll be going through the thermodynamics of gas in liquid solution. So first of all, imagine that A is a solvent, A, or I want to tell A is solvent, which is your liquid. I want to call it as 1, and B is your solute, which is a gas. So I want to call this as 2. So what you're discussing right now is gas dissolved in liquid. Okay. So first let us see the effect of pressure here. Or thermodynamic derivation of Henry's law. Now if this is stable, so which means that an equilibrium has reached. So at the start let us start assuming that an equilibrium has been reached between. It's not an assumption, we take it for granted. Unless if when it is stable, it means an equilibrium has reached. Between the gas in vapor phase and gas in liquid solution. Here between B and B. Okay, so between these molecules and B molecules in the liquid. So if an equilibrium is reached, so what do we say is that, see here 2 represents, as what 2 represents the solute, that is gas, and 1 represents the liquid. Okay, so if I tell that equilibrium is there, so it means the chemical potentials of 2, that is in solution, at temperature, pressure, and its amount fraction, that is mole fraction, should be equal to your chemical potential, okay, of the pure vapors, gaseous state, at certain temperature and pressure. So we start here. If the solution is considered to be ideally dilute, we have seen in the previous derivation, okay, that this of any mu of A, a general derivation we have already done, is equal to mu A star plus, that is liquid, plus RT ln XT. Okay, so if I have to, this is general, this has been derived in the previous videos, you can just go back. That is the chemical potential of A in a solution is equal to chemical potential of the pure liquid plus RT ln XE. So now if I have to generalize this, your mu2 solution at temperature, pressure and x2 becomes equal to your mu2 liquid plus RT ln X2. Fine. So this has been taken care. Now what is this equal to? So this, if gas is assumed to be ideal, so this also has been derived. Okay, so now both have to be equal, right, according to the equilibrium conditions. So I can equate both of these two things. This is equal to this according to the previous this equation. Okay. So I'll write now if I do little maths work here, what I get is x2 divided by p by p naught is equal to T. Now at constant temperature, what happens is R is a constant, T is a constant. Both of these are constant. This is chemical potential of a gas at pressure, standard pressure P naught of is equal to 1 bar. This is a constant, which is the chemical potential of a pure liquid. So therefore, this is constant, this is constant. The right hand side seems to be constant. So what I'll write is at constant temperature, ln x2 P by P naught is equal to a constant. Now I'll do some work here. X2 divided by P by P naught. I'm taking it. So this is again a constant. E to the power constant is a constant. So x2 into P naught by P is a constant again. And what I'll do is x2 into I'll put it this way. So x2 is equal to constant by P naught into P. Or let me not go ahead with this. Let me put it here that x2 into P naught by constant is equal to P. Right. So now P naught is a constant. This is a constant. I can write it with a new constant, which means P is equal to. I call this new constant as x2, and I want to call this as Henry's law constant, and this law as a Henry's law. So I will do it. It's P2 by P2. I mean by P. I mean P2 here. So just make this. It's understood, right? P2. We are talking of a solvent. So it is P2. Okay. So this is your Henry's law. The same thing can also be written in terms of, so this is in terms of amount fraction. Henry's law in terms of okay, I can also write in terms of mass here. The same thing, let me do it in terms of mass. So I bring back again these two things, x2 into p naught by p2 is equal to constant. So which means x2 is equal to constant by p naught into p2. Oh, okay, yeah, same thing. So x2, this is a constant, p naught is a constant, x2 is a constant into p naught. For a dilute solution, x2 is equal to what? N2 divided by N1 plus N2. So for a dilute solution, what happens? N2 is negligible compared to N1, so it is N2 divided by N1. So what is N2? N2 is mass of 2 divided by its molecular mass, right? And N1. And this I can write it as 1 divided by M2 into N1 into M2, right? So that is x2 is directly proportional to m2, and since, so I want to write x2 is equal to some constant dash into m2, and I want to equate both of these two, this equation A and this equation B, and tell that constant dash into m2 is equal to some constant p2, and m2 I can write it as this constant divided by this constant dash will again give me another constant which I want to call it as kp2. Okay, so k is constant, so this is your Henry's law, new constant. So this is Henry's law. So which states that the solubility of a gas in a liquid is directly proportional to the pressure too, which means the solubility of gas in a liquid increases with the increase in the pressure of the gas. So let me write that. So the law states that at a given temperature, the mass of the dissolved gas in a given volume of solvent is proportional to the pressure of the gas with which it is in equilibrium. So if m is the mass of the gas dissolved by the unit volume of the solvent at equilibrium pressure P, then according to Henry's law, m is directly proportional to P and m is equal to K P, which where K is a constant of proportionality. So more about this K, we will do it in the next video. Thank you.